this is homework B1, in which I'm going to derive or change our equation of state formula, which is a cubic form, into our cubic root equation. So first, as you see here, we have P equals RT, that's an R, over V minus B minus A over V plus epsilon B times V plus sigma B. So the first thing we're going to do is we're going to try and write this in terms of compressibility. And we learned that the compressibility equals, let me write it over here real quick, PV over RT equals Z, which is the compressibility constant. And so we're going to multiply by V over RT, which would lead us with Z equals V over V minus B. Yes, because these RTs would cancel. We subtract, and then we're going to have A over, will be A times V over RT. Then we would have, that would just be the only change. It would be V plus epsilon B, and then plus sigma B. So now that we have it equaling Z, or gas constant, we can do a little finagling and make it look a little bit prettier. It's going to look ugly before it looks pretty. So we're going to have Z equals 1 over 1 minus B over V minus AV over RT. And we're going to factor out this V. So it's going to be a V squared 1 plus epsilon B over V. Now we're going to repeat that step with sigma. 1 plus sigma B over V. So as you can see here, our V's here will cancel. So we have 1 over 1 minus B over V minus A divided by RT over V times 1 plus epsilon B over V plus, or multiplied by 1 plus sigma B over V. And so we want to get rid of every B that we have in this equation, or V, sorry, not B. And to do that, we can change our gas equation again. So we can have this as V equals, so we would just do Z RT over, over pressure. So now we have changed what our V will be. Let's actually apply it. Okay, I just want to make sure I was still recording. So we have Z equals 1 over 1 minus B P over, excuse me, and then that would be over, I want to say, excuse me, let me just look, over ZRT. And then that would be, then we would subtract, it would be A over RT, and both of those would be squared, and then we multiply by Z, 1 plus epsilon beta, then we would also multiply pressure, again, over ZRT. Then we would just repeat the process. Oh, I just copied it. I didn't actually change the equation. There. Over ZRT. And now that if you notice, while looking at our formulas, we have a few things that keep popping up and popping up. We have BP over RT, and that pops up a lot. And so what we're going to do is we are actually going to abbreviate that. So we are going to have beta equal BP over RT. And so now let's rewrite our equation over here. So we end up getting gonna try and draw a little line real quick. Z equals 1 over, oh jeez, man, I need to focus on what I'm writing. So we get 1 over 1 minus beta over Z. And then you would also get, then for the A term, we would have A over, let's see. Oh, I forgot to change, I forgot to add pressure up here. Yep, so we would have A times 2, sorry, let me just look through this real quick. So if we have, we're trying to have B. So yes, we're going to have to multiply this by B, I believe. Or so we don't have a beta on the top, but we do have pressure. So to get this, we would still have R, T, Z, minus, not minus, excuse me, sorry, I'm just trying to think real quick. I'm having a little small brain fart. But let's just forget that for now. Then we would have 1 plus epsilon, okay, so make sure you can see, epsilon BP over Z or T over Z, and then same with sigma. And so again, let's try and figure this out. So we have A, P, and so over RT, R squared, T squared. So we know the bottom would be right. We know we would cancel out 1R, 1T. But we know A would remain as well if we have beta. So we would have, maybe I didn't mess up without transferring the P. Well, here, let me look back again. If we plug in RT over here, we're going to plug in whatever we have from V. So we would get then V squared, just have 1V remaining. And if we want to change V, V would be then times Z times RT over P. And so if we had that over P, the P would be up here, I believe. Yeah, so that would be like that. We could just flip that. Sorry about the jump cut. My computer actually shut down. So let's get back to where we started. So we realized that we have AP over RTZ squared, which then led us to believe that we are going to, because we have a V, or because we have this, we are going to abbreviate it into a B. And so to do that, as you can see here, we have A times P, and for B, we need to have a B. Or for beta, we would need to have a B. So we would have to multiply this by A times B times beta. But another thing we realized is we don't like having the RT on the bottom. This is the only place in the equation we have RT, along with A, and actually this B. So what we're going to do is get lazy again. We're going to create this function Q, in which Q is going to equal A over B, and then over RT. So that way, when we come back here, we can rewrite this as Z equals 1 over 1 minus beta over Z minus, then we're going to have Q beta over Z 1 plus epsilon Z, and then 1 plus sigma B. Not sigma B, sigma over Z, excuse me. So in this equation, right now we have Z equals 1 over 1 minus beta over Z. Then that entire function we're going to subtract by Q times beta divided by Z times 1 plus epsilon over Z, or times 1 plus sigma over Z. And if you notice something, we have a lot of z's in the denominator. And so what we're going to do is we're going to multiply this whole function by 1 over z. So what this does is on this side of the equation, we have z over z equals 1 equals 1 over z minus b, or minus beta, not b. I'm going to keep making that mistake, but it's not true, it's not the same. Minus q, then beta, over, if we have z squared up here, we can actually distribute. So we have z plus epsilon, and then we have z plus sigma. And this equation is how we're going to start to cross multiply. So I'm going to erase this side, and I might write this bigger if it is harder to read. And I will write that bigger so we can start to cross multiply. So here, I'll rewrite that real quick. So we have 1 equals 1 over z minus beta minus q times beta over z plus epsilon and z plus sigma. So now what we're going to do is we're going to cross multiply. But before we do that, I'm going to figure out what this ends up being. That way it's easier. Instead of having 3 terms, I'll just have to multiply by 2. That way it's easier to do in your head or just while looking at it. So we have, over here, so I'm going to make a box because that's how I was taught to do this a long time ago. So we have z plus, did I forget something? I forgot to add the betas here. There were supposed to be betas here, which means that's beta, beta, beta. I think. But yeah, that's right, that's right. So we have z, and then z, then we have sigma beta, and we have epsilon beta. So we get z squared, and we have, we're going to put the z's at the end of the term. So we have sigma beta z, we have epsilon beta z, and we have epsilon sigma beta squared. So let's start to cross multiply. So we have z minus b. Then we're going to multiply that by this funky looking equation. So that ends up being z squared. And then we have, both have bz, so we can do, we're going to add, we're going to have sigma and epsilon. And that ends up having a bz multiplied by each. And then we're also going to add at the end epsilon sigma beta squared, which sounds like a fraternity. Okay, and this is actually the left side of the equation, so we're going to write left, and then the right side of this equation is going to be this minus this times this, which this is kind of hard to explain, so I'll write it down. So we end up getting, okay, making sure we're still recording again. So we end up getting z squared plus epsilon sigma bz, or beta times z plus epsilon sigma beta squared, and which we then subtract q times beta multiplied by z minus b. Okay, so this is the left-hand side, and this is the right-hand side. And what we're going to try and do is we are going to separate these onto all on one side and get the coefficients. That way it will be easy to calculate the roots of this equation. So I'm going to erase everything over here and then do it a fun, little funky, nifty way. Okay, so the way that I was shown was in class, and this seems to be the fastest way of doing this. So we're going to have z cubed, we're going to have z squared, then we'll have z, and then I'm going to put 1 to represent no z. And so for z squared, or for z cubed, let's look at this equation. So we have z times z squared, and then nothing else on this side of the equation multiplies by z squared again. So we're going to have a 1 in this column. Okay, now we calculate the coefficients of z squared. So we have a z squared, or we're going to multiply by the z. Okay, so we don't have anything there. And now we multiply it by over here. We have bz multiplied by a z is going to have another, it's going to be b times z squared. So in here, we're going to have epsilon plus sigma beta. Okay? And now we're going to multiply z by this equation. So, oh, this is going to get full very fast. So we have epsilon sigma beta squared. Okay? And now let's multiply by our negative b. So in our z squared, we're going to have negative b. Yeah, just negative b. Oh, geez, that's ugly. First, it's going to be negative b. And now if we multiply negative b times this, we end up getting negative epsilon plus sigma beta squared z. So it's just going to be beta squared. Okay? And now we have negative b times this. We end up getting negative epsilon sigma beta cubed, which is ugly. So that's all on the right or the left-hand side of the equation. So now, this is going to be, I'll write this again. These were all the coefficients on the right. No, on the left. I keep getting these mixed up. So this is on the left. And this is on the right. R-I-G-H-T. There we go. So, we look on the right-hand side. What we're going to have is we're going to take everything on the right over to the left, as we want this to equal 0. So all of what you would think would be the coefficients, just make them negative. So we start with a z squared, and then nowhere else do we have a z squared. So we're going to do so first our z squared is going to be 1. And then we have epsilon, and this is a z, so we're going to do epsilon plus sigma times b. Okay. Oh, don't forget to make that negative. I forgot. Make these negative, remember? Just spoke about that. And now we have this again. So epsilon sigma beta squared. We're going to make that negative. So epsilon sigma beta squared. And now let's get over here. So we have negative Hw2B times z. So it's going to be negative Q times B, but because it's negative, that's going to mean it's positive. So we're going to do that. I definitely didn't forget. And now the last term in this equation will be negative QB times negative B. That will equal positive QB squared. But because we're going to bring it to the other side, it's going to be negative Hw2B squared. And this is all of the work needed to do to start to find your roots and change our equation from what we originally had in PV and RT form. We are able to derive it into our terms of Z. That we get rid of any volume that was in our original equation. And yes, we have our abbreviations of B or beta equaling BP over RT, and this is what we did to get rid of our V. And don't forget about Q, which is A over B times RT. However, none of those have volume, which is kind of our main focus in this equation.
Hi everyone. So in that previous video, or the previous clip, we found the derived equation in terms of Z, or a cubic equation in terms of compressibility. So what we're going to be doing right now is we're going to be writing a equation so that we can calculate the roots of a cubic polynomial. This is important as this can, if you can think of it, think of the graph, you can give us the roots and how many points there would be on said graph. This is again really important for future parts when we try to integrate. We're going to need those specific points. And so, let's get into it. So I'm actually writing my code on the A3 part as we're going to be using them to check each other in the later videos. But as I stated earlier, I'm going to show you a picture or a screenshot I took of an equation that will help us factor cubic polynomials or find coefficients. So we want to calculate A, B, and C, okay? And that means we're going to want to return A, B, and C as those are the roots or not the roots, those are the coefficients of what we're going to calculate. And that will help us find the roots. So we're going to want to define cubic R, and then A, B, C. And now there's two different terms. There's R and Q. However, R is already being used up here for a different value. So I'm going to calculate this as RR. And then this is going to be Q. So Q equals A squared minus 3B over 9. It's going to be A squared minus 3 times B. And now we're going to divide that by 9. R, on the other hand, is a little bit longer. 2A cubed, so it's going to be 2 times A cubed. And then we're going to subtract by 9 times A times B. And then we're going to add 27, multiply that by C. And then we're going to divide the whole thing by 54. Okay? And this states that if Q and R are real, which is always true if and when A, B, and C are real, and R squared is less than Q cubed, then the cubic equation has 3 real roots. So that's going to be a if statement in our problem. So if R squared is less than Q cubed, gotta put that, theta is equal to arc cosine of R over the square root of Q cubed. I hate saying Q cubed. I'm gonna mix it up so many times. But this also is equal to 1/2. Or not 1/2, is equal to 3/2. As it's 3, then basically if it's a fraction, if it's a exponential, you can kind of divide by the powers. So you get theta equals np dot arc cos, right? And then we're going to have r, and it's going to divide r by q to the 1/2 power, or 1.5 power. And if this doesn't end up, if we get in any issues with this, I can always change this to the square root and then have q cubed inside of that square root. And once we have that, we want to return our root values. So, because these are A, B, and C. So if you notice on all of them, we have -2 square root of q cos. So we have negative, and we're going to want to return -2 times the square root of q. And then we want to multiply that by the cosine of, we want to keep all of these variables in like the same A, B, and C that we're using through. So we're going to put that into an array. So it's going to get kind of nasty as B dot array. And so in that array, the first term is theta divided by 3, theta over 3. The next term is, so actually this is something I want to clarify real quick. So when we did this, we were shown that this second root is actually bigger than the third root. And so I guess that you might be able to see that by looking at the equation. So we're going to switch x2 and x3 in the equation. That way it's just easier for us to look at. So next we're going to do theta. So it's going to be theta minus 2 np pi. Let me see if this is right. Yeah, np pi. And we're going to multiply that. And then we want to divide the whole thing by 3. Okay. That works. And another thing, you see we have minus a3 on the end of every one of these roots. We're going to put that at the end, kind of how we put negative 2 square root of q on the front end. So that's the second root. Now the third root is going to be the same thing. We're going to add. So it's going to be theta plus 2 times np dot pi divided by 3. We're going to do that real quick. Okay. Let's just look at where these parentheses go. So this closes the array, and this, so does the parentheses. And this parentheses is at the end of the cosine. So the next thing we want to do is subtract a3, or a thirds, minus a divided by 3. So that should be our first bit of this. Now, let's go back. Not that. Let's go back to that picture. Jeez. So, actually, I have another picture that shows the bottom part of this. I couldn't get all of it in one picture, so let's go to my files, and then we're going to go to pictures, save pictures or camera? I think no, screenshots. Yeah. There we go. And now let's go back to what we're working on. So this says that otherwise, which means we're going to put that as else, a equals negative r plus square root of r cubed minus r squared minus q cubed to the 1/3. And so something I've had issue with already before is actually putting that 1/3 power around. So we're going to do 1 underscore third equals 1 over 3. That way we can we won't have issues with that. So now we're going to go else. Let's see, does this have a bad indent? Maybe let's try that. Yeah, there we go. It says expected indented block, and then expected. Nah, we'll worry about that later. Anyways, we have a equals negative r plus, okay, negative r plus this np's at square root, or, no, not square root, we're going to do plus r squared plus, is that plus, right? Minus q to the third, and the 1/3 goes around everything. Power, by the way. So now we're going to do the power of 1/3. and hope that works. So now if what this is saying is if the positive square root is assumed, next compute b. So we are going to have, I believe this is going to be another if, or we're going to go back to the original. So let me see if that works. Okay, we're going to undo that. Now we're going to do if, well, so b equals 0 if a equals 0. Else b equals q over a is what I want to say. So we're going to do if, not f, we're going to do b equals 0 if a equals 0, which we've already calculated a. Else b equals q over a. So, let's see what's the issue. Expression cannot be, okay, let's see if this works. Oh, it expects an else. Expected else, okay. So, let's see what it wants. Else. This is expected expression. It says expression cannot be assignment target. Okay, so let's work through this. So we're trying to say if a does not equal 0. Actually, I can do this in other way, but might work. So we're going to do if a equals 0, then we're going to do, sorry, then we're going to do b equals 0. We're going to do else b equals q over a. Again, I think this could probably all do it in all in one line, but this might be easier just for me. And we want to return, because we're doing this if this isn't, if r squared and if this isn't true. And so now that we have this, we're going to say our only true root, so now we're going to return again. No, I should do this. Return a plus b minus a over 3. So, yeah, that's worked so far. So one way to test this is, oh geez, I didn't do that, is we can do p equals np dot polynomial dot polynomial module provides a number of objects. Let's see what happens if we put the roots as 1 dot, comma, 2 dot, comma, 3 dot. Oh geez. Let's see, what's the issue? Let's try this. Let's try cubic r of 1 dot, comma, 2 dot, comma, 3 dot. No, sorry, I'm thinking of something else. So we do -6, comma, 11, comma, -6. As if this would break or not. Oh, that's not great. Okay, let's keep going through this, trying to figure out what's wrong. I think I'm having a few issues with my Google connection right now, as I get a few blips of where certain functions won't go through. However, I think this might be messing something up. So let's see if that works. Okay, I didn't change anything. Okay, so we have our 2 times A. Let's try this again. 2 times A cubed minus 9 times 8 times, look at R, it says it's 9 to the B power, but it should be 9 times A times B. So that might be a thing. So the first root is right, or the second root is right, the other ones aren't. That's interesting. So let's work through this. So we have plus 27C, and all divided by 54. Cubed is A squared minus 3B. Let's just get rid of that and see what happens. I think that might be an issue too. Oh, look. We got 1 times 2 and 3. Let me just try and prove it to you. If this won't load, I will call it. But so we do P equals NP dot polynomial dot from roots. Now it wants the roots. I'm not sure if it wants them in an array. So let me try them without an array. So 1 dot 2 times 3. Okay, yeah, it looks like it needs to be in an array. Oh, geez. Let's stop that. Or if you put an array, yeah, that goes inside. Now let's try and see P. What is P? It says an error. Well, so that should be right. So let's just see what happens. I want them to show me P. I've been having this error a little bit with code, however, not in the professor, with code laboratory recently, but I think it might be my connection. My computer is getting old. Okay, it looks like it's not going to work. You're going to have to trust me. This is how, or this would be the coefficients, and then this would be right. So that's good. This allows us to take the different types of roots in our polynomials, and this really helps with van der Waals, or even, oh wait, I just found an error. Oh, I mean, it didn't affect us, but it could have. So this is, that's a different thing. You see here, this is r plus the square root, and then it's 1/3. So this would be, yep, see, it says this is probably visual count, but this would be to the 1/2. So again, that doesn't affect us because we have all 3 row roots, but that could. So from here, again, as I was saying, this helps us a lot with different ways of finding roots, and it's good. Now we can start to work on our integration and how SRK works. So now we're going to be doing part V3. I'm going to try and separate it into a few different smaller, more manageable parts. So it states that using V1 and the parameters for the SRK BOS equation state, use V2 to determine the limits of integration for the maximal equal area construction, estimate the vapor pressure of water, and using that, estimate the vapor pressure of water at 373 Kelvin and compare with the expected values. So what I'm first going to do is I'm going to create a dictionary so we can determine, so we can calculate the pressure if it's specified as van der Waals or specified as SRK. Or, yeah. And then from there, we're going to use that to calculate the volume at which we can, we're going to use that to calculate the volume much like we did here, and then we're going to compare, and those will hopefully be correct. After that, we are going to calculate the volume. And we're going to calculate the volume for which that the temperature is going to cross the line. And then from there, we can use our integration squirrels and determine the limits of integration with Maxwell equal area construction and look at the areas and what those will tell us. So first, we're going to create our dictionary. So what we're going to do is we're going to define this as, I'm going to call this should we call this SRK, VW, or we're going to call this EOS, ABC, not EOS, so we're going to use that already. We're going to call this ABCD, ABES. Yeah, we're going to call this ABES. And granted, that's going to return us A, B, E, and S. So I have this picture here, which gives us a lot of different information, but I want us to remember the actual equation for van der Waals equation state, which I actually don't have pulled up real quick. Which this will do. So this is the equation state we're using, but we are actually using RT over V minus B minus A of T over V plus epsilon times B multiplied by V plus sigma times B. So first, let's look. We have R, T, V, and B, and then A, E, epsilon, and sigma. Let's do sigma. So we're going to have sigma equals, let's try this, and that is going to be V dW, and we're going to call this, for VDW, let's look at our picture. Sigma for van der Waals equation of state is 1. And now if we do SRK, no, we want to input T and then EOS, or equation of state, and that's going to equal, by default, SRK. Okay? And SRK is going to equal 0. And this will only happen when we refer to EOS. So, okay, that works. So I'm going to test it just to make sure I have this loaded right. So we're going to say S. I don't know how to test this without actually writing out the full thing. So let's try S or return S. I'm not going to save. Oh, crap, I'm not going to issue again when that thing doesn't run. No! I don't want to have this issue. Anyway, we can mosey on. So now we're going to do epsilon, which equals van der Waals, VDW, V equals 1. That's the wrong. Yes, epsilon. No, sorry, epsilon equals 0 for both. So this is the wrong type of bracket. We want the bracket with the pointy ends. I don't actually know the scientific name for that. So we have that. Now we're going to do SRK. That equals 0. Now we're also going to call it EOS. Okay. Now, the other things that we have in here are omega. So, omega. So what we're doing here is, what we did earlier in A3 is we hard-coded van der Waals equation of state. What we're trying to do is create a equation of state where you can pick either van der Waals or the SRK. That way it's easier in general terms. Or in testing, you can see the differences. So when we VDW, and that equals 1/8. See, what's the difference here? We'll keep going. And then SRK. Oh, I see. Do you see the And so SRK, I think this one's pretty ugly. It is 0.08664. So there's that 0.08664. Let's make sure we have that right. 0.08664. Okay. EOS. And let's see what else we need. Psi. Yeah, psi. PSI. Like the rapper from that old Korean movie. Korean video. BGW. I'm pretty sure that equals 27 over 54. No, 27 over 64. Okay? And now we have SRK, which this one might be even uglier than the previous one. It is 42748. 42748. EOS. Okay? So we have epsilon, sigma, omega, psi. Now this is going to be alpha. But to calculate alpha, since we need TR, and so TR equals T divided by TC, I believe. I wrote that down over here just to make sure. Yep, T over TC. Okay. And now we have, we're going to call this alpha. This one's going to get really ugly, just a heads up. VDW is lucky, as it is 1. However, SRK is, it's a long one too. It's 1 plus, well, you see we're going to need a W term, but I'll get to that later. It's 1 plus 0.48 plus 1.574 times W. Actually, let's get this up here real quick. So W is the eccentric factor, and in the video we were shown, we used 0.348. However, in my Googling, I found that the eccentric factor for water is 0.344. So I'm going to be using this, or actually, I'm going to be using what we did in the video. However, at the end, I might go back and change it and see how this affects our problem. So we have 0.348. Okay, we're going to save that. Okay, now that we have W, let's look back at this. So it's times W minus 0.176. 0.176 times W squared. 176 W squared. Okay? And then we multiply that. We multiply that by 1 minus square root of TR. 1 minus TR to the, let's try this, 1 over 2. So let's look at that. Let's change that. I don't like that TR's uppercase. Okay, so we have 1. Let's try and see if I can make this smaller. Or skinnier, that works. So we have 1 plus 0.48 plus 1.574 times W minus 0.176 times W squared multiplied by 1 minus TR to the 1/2 power. And now it says that this entire thing is raised but let's see. If it goes out here, so this is the only thing. Yeah, so then this entire thing is squared. So now we have alpha. Let's look at beta. So beta is omega. Now this is something that's not unique. So we're going to beta equals omega times R, right? Omega times R times TC. Let's uppercase this. So it says it's R times TC all divided by PC. Okay? And the last thing is we need our A value. So A, would this change? No, it would not change. Just what we're going to do is say, well, alpha would change depending on what we're using. So because psi is different, our alpha is different. However, what we would do is we would select a value, and so it would bring just those values down. So it shouldn't affect anything. So we're going to have A equals psi. So then I'm going to change to psi times alpha times R squared times TC I believe that's TC squared as well. Okay, yep. And the reason I'm not going to put these all in a giant parentheses when I divide is because it's all multiplication, which means it's not like I'm going to have any issues like I did down here with addition or subtraction. So, okay. Now that we have our values, what do we want to return? We want to return, well, so I call this beta, but I think I might just call this B. That way it's easier. So we're going to return, can I do this in parentheses, or can I just do A comma B comma, no, let's see, A, B, and E comma S, as those are the things all in our equation. Let's look real quick. So we have A, B, and then E and S would be down here. So I'm changing this to lowercase b. That's going to annoy me. Okay. So now let's run that. No errors so far, but they will come. So we have going to define our function as we're going to calculate the pressure. So define, we're going to call this cubic P, and we're going to put in temperature, or let's see, we're going to put in the volume, and then the temperature, and then, would you need to put in volume? Let's think. So, volume, temperature, and then you have to put in EOS. Yeah, I think you will need to put in volume. So let's just, we're going to say V, T, and then we're going to do EOS equals SRK. And what this is doing is, all it's saying is we're going to pull from SRK unless we're told not to. Let's see, what is the issue? Why does this have an issue now? Let's look at indented block. Well, we can worry about that later. So we want to have A, comma, B, comma, B, comma, S, and those are going to equal A, B, E, S, T, comma, EO. Not EO, no, we're not going to put, we're just going to put EOS, because if we put EOS equals SRK, that means it's going to draw on them no matter what, and that could be bad. As if whatever you try to do van der Waals, it's still going to pull an SRK, so this EOS is just going to be there. And now I really want to know what this issue is. Some might have, that's just saying it might have changed. Who cares? So it's going to be, what was the equation? So it's going to be R times T divided by B minus B, right? Okay, lowercase b, right? Now we're going to be minus alpha, or not alpha, just A, divided by V plus epsilon times B, multiplied by V plus sigma times B. Okay? And, okay, now let's try this. I'm going to do that. I'm going to try and run a code and see if they are the same. So make sure everything's good. So we want to use cubic P. We're going to try this with van der Waals first, so we can try and test these. So we used 1 and 400 down here. So do cubic P, 1, comma, 400, and then we're going to do EOS, which equals VGW. Oh no, I'm going to get the issue where nothing loads. But maybe if I refresh the page, that might work. Okay. Let's see, where's the issue? I'm really having a hard time with that co-laboratory. It's just giving me these spinning issues, and I don't really seem to get any resolution sometimes. So maybe if I close it, leave, go to my drive, let's refresh the page. Homework 2, 3A is what I believe you're working with. Not sure if I changed it. Okay. And I'm still getting an issue. Here, I'm going to cut it here and then hope to resolve any issues I find just with this residual just spinning and turning issue. So it's been a little bit of time since last clip. However, I unfortunately keep getting this error, which through some Googling I found it's very difficult to get rid of. So I think this means I won't be able to run every single line of the code, but theoretically what should happen is when I run this equation, when I run a cubic P, you should get the exact same number as what we get here. And if you run it with SRK, you get a slightly different number. but it would be correct using the SRK method. So what we're going to do now is we are going to code our volume equation. So we're going to, and in doing so, we actually get to use what we derived in part B, no, sorry, not B1, and in part B1 is what we get to actually derive and use now. So we are going to define, we're going to call this cubic V, and what you're going to put in, I believe, is the temperature and the EOS, and we are going to assume it's SRK. But we can check what we put in, because I transferred for what we had at the end with us putting it in different columns into my sticky note here. And in our sticky note, we have pressure, our value of temperature. So we may need to also put our pressure in here as well, as we also have A, B, R, G, but we can get the others. So let's put pressure in here as well. So now we're going to put A, comma, B, comma, E, comma, S equals, let's see, what did I put? What was the name of this? A, B, and E, and S. Wow, we should look at that. T, comma, EOS. Okay, so we have this. Now let's call our function ZS, which is going to have all of our roots. This is going to be big, so heads up. So we're going to first start with our Z squared, because what we know with the cubic root is 1. It's going to be x, the third is 1. So we're going to do this. So it's going to be, oh, we have to actually define beta and q first, so this is going to be messy, even more messy. So beta equals B times P divided by R divided by T. And Q is A divided by B times R times T. Okay, now for the fun part. So we have Z squared, it equals E plus S. There's going to be a lot of this, heads up. E plus S times beta. See, if I were smart, I would abbreviate E plus S into a different function, but that's just asking for more issues with co-laboratory. So times beta, and then we subtract 1. Let's put those here. Okay, that's the first bit. The second is going to be E times S times beta squared minus E plus S. Is that beta squared times beta squared again. Okay. Now we're going to subtract. We'll go to surprise. It's going to be E plus S again. I know, surprising. Let's try to not make any uppercases. Plus S times beta minus barbecue. There we go. Now minus B times Q. And that's our second root. And now our third root. So it's going to be negative E times S times beta cubed minus E times S times beta squared beta squared beta squared minus Q times beta squared. So we're going to subtract by Q times beta squared. So this, theoretically, should be our roots, which means we're going to want to return. So if you remember earlier, we had P, what was it? It was RT over PV equals Z, if that sounds right? And so this would mean that for our roots, or for our volume, we would have a volume would equal our roots. So it's going to be Zs multiplied by the temperature, and then we're going to multiply by R as well. Then we're going to divide by pressure. So I believe, yeah. Man, sorry. Because we subtracted everything off to one side to be able to find where the other equals 0. And then from there, we can plug that in to get our volume, which is what we were looking for. As what we did was we solved for something, we solved in zero, no terms of volume, which was our plan. And so this is kind of returning the specific volume that we would like, or that we want. You see, that would work just fine. But if I try to plug anything in, like here, let me try, no, that would break it. So now that we have our cubic volume, our last and final step, if we look at the homework, is to determine, which we just did, the limits of integration, going from here to here, and then from here to here. And then from there, use Maxwell's equal area construction, because if you remember from our last, or from A3, which I don't actually think we can try, this is able to run it right now. Yeah, it's not going to work. It's going to get the same error. We had a funky little curve where if you put our line through it and you have equal areas, that is the, I believe that is the vapor pressure, or what was it again? That's the, if they're equal, you can estimate the vapor pressure, and then you can compare that with the expected value that we calculated. So now we can work on that. Now we're going to be doing the last part of this problem, in which we are going to get the limits of integration and estimate. Well, theoretically, because unfortunately, I'm still running into the specific and fun error. But if we want to integrate, we're going to have to import something to help us. So we're going to have to import side, or is it, no, it's from, I think it's, yeah, from side pi dot integrate. We're going to import y. I mean, it would help if I could spell. And that doesn't break anything, so we're good there. So something I realized is that we are going to want, or I actually had an issue, or I did something wrong. This is b here, and this should be beta. And so that's just another place we always want to make sure we're checking the mistakes. So we are going to create our function for the Maxwell area. And so in that, we are going to have, this is a pressure, and then a temperature, because we want the volume. And then we're going to have whichever, yeah, see, we get this issue again. And we say we're going to want an EOS. We're going to assume it's SRK. But what would that actually affect? So we do, only times we've really assumed we want the different change would be when we're pressure versus temperature, as we are going to be taking A, B, E, and S. Actually, I'm not sure if we need this, but I'll come back to that. So now we want our limits of integration. So we're going to call that VL for V liquid, VM for V middle, and VG for V gas. And all of those are going to equal the three roots, as the way you could make sure these roots are right is you would graph cubic V in place of this equation right here, I believe. Or instead of graphing that, I think you would graph this function right here. And then you would look at the volumes for the specific temperature which you would go through. You say, oh, this is 8 to the negative fourth. That lines up on this graph. This lines up here. And so it cuts like a clean across. Or you're right when your temperature hits all of those points. Man, my hands are cold. So we would have that equal to cubic, actually this makes me think we don't need this. This would equal cubic V, in which, we need P, T, and then EOS equals SRK, or, again, I don't think we need this because, do we even need EOS? Let's see. What did I put up here? That way, we don't always pull EOS. So EOS is actually just works by itself here. So, however, this says EOS is not defined. Why would that be? Well, let's just keep looking again, just real quick. It's because we're using the function. But if we were to use this function, okay. No, we'll keep it, screw it. And now we would just, these are our limits of integration, so we would just integrate. So we would do, let's see. Oh yeah, we would return. If I could spell. And we would do lambda, which is a way of having a function without actually using it. And then we would do pressure minus our, I think we would do, minus our cubic volume. What would be minus our cubic pressure? Because this is what we would graph. So I would think we would do minus cubic pressure, which is VT EOS, V comma T comma EOS, and that would be our first equation. Well, that would be what we would want to integrate, and our terms would be VL to Vn. So it says EOS is not defined, but okay, that makes me think we don't need it, so screw it. Now we would also have we need this to close it off, I think. Then we would also have lambda V, which we have cubic P, let's try V comma T, minus the pressure, as this is when it goes, say we have a cross, we're going to go, and then we're going to go the other way, so it's going to go, I hope that makes sense. And then our limits of integration would be Vn as the lower end to Vg. And that should be good. And so what we would do is we would use, let's try, oh my gosh, not this again. Sorry, I'm going to stand up real quick and wave my arms and hope. Sorry for the abrupt cutout again. My computer has given me the blue screen of death for the 4th time today. But let's get back into it. So this, in fact, does need an EOS confirmation, while this does not, as we're pulling it from something, so we don't need that. But this, again, does need the EOS confirmation, as how are we going to know what we're going to drive, or how we're going to pull from it? So EOS equals SRK, or maybe it's just EOS, but let's try SRK. another thing is that we didn't actually use quadrature. So quad is what's actually going to integrate this function. So we have quad, which is then our function, and we have a and b. And let's see if this function actually works for me if I just get this spinning. If I just get this spinning. So we'll do Maxwell area. We'll do 1 e to the 6th, and now let's do 600. Okay. That's actually a good sign. Maybe this is going to work. Oh, wow. Everything is working. But now we're having issues all the way up here. So unsupported operator types for this multiplication sign up here, it says. Or cubic P. Okay, so there's a few errors. So cubic P 400. Oh, I didn't put EOS at the end of this. But man, this is EOS. Okay, whoa, that's good. Look, it's the exact same, so we don't have to do theoretical anymore. This is like a Christmas miracle. So that's good. And from here, works. Now let's see what the issue is. So we can't multiply sequence by non-iterable type of float. So let's see, what does that mean? It means we're getting some type of error here. So it says, we got pretty far, so that's a good thing. So we can't multiply sequence by non-iterable type, which is a float. So 2pi. Maybe because it's multiple different factors, but I don't feel like that should be an issue. 2pi, number. Should this be an array? Let's look at this. So we have that. So it's all closed correctly. We've got 1, 2, and 3 different values, so that's good. It says can't multiply by non-iterable type of float. So the issue is occurring down here, but I'm willing to bet it's with our ZS term. Oh my God. I'm supposed to take the roots of this, right? These are the roots. I never used my function. Oh my gosh. So what do you, cubic R and if, I feel like looking back at it, these shouldn't have SRK because the function we're already using already chooses the type, and we only need it here because we need to choose whatever the type is, but this is already pulling from something that's chosen its type. If that makes sense. So let's see, it says it's divergent or very slow. So this is the pressure and this is the temperature. Let's try something else. Let's try 3 and then let's try 373. Let's see, what else do I need to change? If I need to change anything? Nothing. So if I go So I was going through this, right, and let's try this again. So we do Maxwell area. Let's just do 13 e to the 6th, and then maybe 600 under this. And I'm getting numbers now, but before, I was getting divergent, it wasn't working. And so I was slowly piecing through my code. Like, let's say I run this again. This is what I had before. And these numbers, which then you change it. Oh, it didn't change it. But the roots, it really messed up the roots, right? And so I'm going through, and I realized that I switched these up. It should be van der Waals equals 0, and SRK equals 1. And this changed a lot of the code. Just, it didn't change van der Waals because one of them is 0, one of them is 1 for SRK, and the other, they're both 0. So it really wouldn't change that. So it was kind of hidden within my screw up. And so when you scroll through, that was what was changing these numbers so much, because they're going to be the same now because I was testing it. And that's what was leading us to getting divergence. But if you see here, we're getting two numbers, and this is the value that we get, that we want, the area, and this is the error percentage. So what we do to get rid of that second number is we only want the first. So to do that, we do 0. That just shows that we only want that first number. So we run that. Oh, crap. Let's see, it says unexpected EOF while parsing. Okay, well, it's just not. Oh, that got rid of that, which then got rid of that. There we go. So now we are getting 1. So these are the area differences. So we can mess around and make one bigger or the other, but we want to get them equal. This what we want is the vapor pressure. So the homework asks us to estimate the vapor pressure at 373. So 373. And so we know it's around, let's do 100 e to the 3rd. Okay, it's close, but this is bigger, or this is smaller than this, so let's take it down a little. Let's try 95 and see what that does. Okay, they're closer, but this is still bigger. So let's try 94. Okay, 93. That's really close. Let's try 92, see what happens. Okay. Wait, how much of a difference is that? So this is 155, and this is 109. So this is 155, and this is 76. So 109 is closer. Right? Yeah. And so now let's look up the vapor pressure of water at 100 C. That's basically what we're calculating. So it equals 1 atmosphere, otherwise known as 101 pascals. And so I would say this is really close in terms of scale of what we were working with. And so, yeah, that was the issues with my code that you were able to see and how they were miraculously resolved. And this is the end of homework 2.